Okay, in this video, I just want to talk a little bit about computing a surface integral of a scalar field. I mean, technically, this is the type of stuff that we talked about really a couple of exams ago, but I want to mention it. Because it has applications to Stokes' theorems questions. Okay, so first, let me just remind you. So this is actually going to be about a line integral or surface integral of a vector field. So if I have a surface integral of a vector field, this is equal to, essentially this is by definition, the surface integral of the scalar field f dotted with n, where n is the normal vector. And of course we have to take things like orientation into account. And given a parameterization, we know how to compute n. N is going to be rs cross rt. Okay, but it doesn't depend on the parameterization. A normal vector is something that's more intrinsic to the surface itself. Okay, so now I want to discuss the following situation. So let's say that S is a region in the plane. Let's say Z is equal to 5. Okay, and now similar things are going to be true for Z is equal to 0 or Z is equal to 17 or even X is equal to 5 or whatever. Any plane that's parallel to one of the coordinate planes. So S is a region in the plane Z is equal to 5. And let's say we want to compute the surface integral of some function f of x, y, z, ds. Okay, now let me sort of sketch what this region might look like. Okay, and it can be any region, so I'm just going to draw a very generic region, R. Okay, S is a region R in the xy plane, and really what I mean to write is this is the surface S. Okay, so when we want to do this integral, the first step would be to come up with a parameterization. Okay, so I'm going to pick the easy parameterization. I'm just going to say R of ST is equal to ST, and then Z is equal to 5. Okay, so this is the parameterization, and in the parameterization domain, it's going to be S and T inside this region S. Okay, so this is kind of like the x-axis, this is kind of like the y-axis, but this is all happening in the plane Z is equal to 5. Okay, and so the parameterization is just going to be R of ST, where S and T are in this parameter domain S. So S is both the surface, and we're using S to denote both the surface and kind of a parameterization domain. I hope you can follow that. It might be confusing, but I think you know what it means. Don't let it confuse you too much. Okay, so what's going to happen? How are we going to do this integral here? Well, remember we need to find RS cross RT and take the magnitude of that. So this is I, J, K. So RS is going to be 1, 0, 0. RT is going to be 0, 1, 0. And if you compute this, what you get is 0, 0, 1. Okay, so RS cross RT is 0, 0, 1. So the magnitude of RS cross RT is 1. Okay, so then the surface integral is going to be the integral over S of F evaluated in the parameterization. So S, T, 5 times the magnitude of RS cross RT, which is just 1, dA. Okay, so the important thing here is that when the surface lies in a plane that is parallel to one of the coordinate planes, in this case it's parallel to the xy plane, then the surface integral, this surface integral is just the two-dimensional integral over this region S of the same function. Okay, because S and T, these are just parameters. We could easily just recall these X and Y. We could just rename them X and Y. Okay, and S and T are in the region S, so X and Y are also in the region S. Okay, and this comes up a lot when using Stokes' theorem, because you'll realize that your surface or the boundary is the boundary of a surface that is in a plane parallel to one of the coordinate planes. That's what I did in the previous video. And I just wanted to say a little bit more about that in this video. And again, like I mentioned in the previous video, you're just going to have to do more practice problems before this can be internalized really well.